A rocket is launched so that it rises vertically. A camera is pointed 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time so that it stays focused on the rocket. You can pause the video and try to solve this problem. Okay, let's solve this problem together. You have a rocket that's rising vertically. That means the angle here is 90 degrees. And you have this camera that is tracking the movement of the rocket. The angle formed between the horizontal ground and the line of sight to the tip of the rocket is variable denoted by theta. And there's a fixed distance between the camera and this point where the rocket is launched, and that distance is 5,000 feet. Let's call this variable as h for the height and the hypotenuse as letter c. Now, based on our figure, we can now compute the ratio between the height and this horizontal distance, and opposite over adjacent side with respect to the angle theta is tangent. So we have tangent of the angle theta equals the opposite side h over the adjacent side 5,000 feet. And then let's solve for h to arrive at h equals 5,000 times tangent theta. We would like to know the rate of change of the height that is attained by the rocket with respect to time. So we can now perform implicit differentiation for this equation. So differentiating with respect to time, dh over dt is equal to this constant 5,000 times the derivative of tangent theta, which is equal to secant squared theta d theta, because we are differentiating with respect to time. Now we need to find what is the value of secant squared theta. It is given from the problem that at h equals 1,000 feet, the velocity is 600 feet per second. So we can now write dh over dt is equal to 600 feet per second. That is the velocity of the rocket with respect to the time, or the change in height with respect to the infinitesimal change in time. Now, since we have here a right triangle, we can now use the Pythagorean theorem in order to find the value of c. The hypotenuse is equal to the square root of the sum of the squares of the two legs. Here, this distance is 5,000 feet and the height is 1,000 feet when the velocity is 600 feet per second. So whatever value for c that we'll compute here, that is the length of this hypotenuse at that specific point when the velocity of the rocket is 600 feet per second. So solving now for c, 5,000 squared plus 1,000 squared equals 26 million. And getting the square root of 26 million, we arrive at 1,000 square root of 26 feet. That is this distance c. Using now this value, and remembering that we are solving for dh over dt given by this equation that we arrived at previously, which is 5,000 secant squared theta d theta over dt, we can now compute for this secant squared theta. First, we need to recall what is secant theta. Secant theta is the inverse of cosine theta. So if cosine is adjacent over the hypotenuse, the secant is the hypotenuse over the adjacent side. So here our secant of this angle theta is equal to this hypotenuse c, which we computed to be equal to 1,000 square root of 26 when the velocity was 600 feet per second. And the adjacent side is 5,000 feet. We want the value of secant squared theta, so we square both sides to arrive at secant squared theta equals 26 over 25. This is now the value that we need to substitute in our preliminary results. So using now this value for secant squared theta, substituting that value to this secant squared theta, when dh over dt, or the velocity, equals 600 feet per second, we can now replace this dh over dt by 600 feet per second. We can now replace this secant squared theta by 26 over 25, and so we arrive at this result. Now solving for d theta over dt, we arrive at a value of 3 over 26 radian per second. Now, what does this represent? This represents the change in the angle of the camera with respect to the change in time. So going back to our problem scenario, this camera should be moving at the rate of 3 over 26 radian per second so that it stays focused on the rocket as the rocket moves up, so that this camera can keep track of this rocket as it moves upward. And to extend this application, this is also how our engineers and mathematicians are performing calculations in order to keep track of missile, in order to keep track of any flying object. And so mathematics is very, very important wherever you go.